Tonight, we drift together into a gentle exploration of time itself and those who might traverse its mysterious currents. You don't need to follow every word or concept. Just let these thoughts flow around you like water over smooth stones. Perhaps you're lying down, eyes growing heavy, or simply seeking a quiet moment of wonder. However you've arrived here, know that this space is yours to experience in whatever way brings you peace. Time, after all, is patient. It will wait for us as we move through this journey together. The evening air is still now. Perhaps you can hear the distant sounds of the world settling, a dog barking far away, the soft rustle of leaves, the quiet hum of your home's familiar systems. These sounds mark time in their own way, creating a gentle backdrop to our exploration. Feel your breathing slow, your shoulders relax, your thoughts begin to quiet as we consider the nature of time together. Time flows around us like an invisible river. We feel its current in the soft tick of a clock, in the gradual shift of sunlight across a wooden floor, in the slow turning of leaves from green to gold. Most of us move with this current, carried forward moment by moment, unable to paddle upstream against its powerful flow. The seconds pass like water droplets falling one after another, each indistinguishable yet irretrievable. We mark their passage with our watches and calendars, our anniversaries and birthdays, creating the illusion that we have somehow captured time, contained it, when in truth it slips through our fingers like fine sand. The ancient Greeks had two words for time: chronos and kairos. Chronos is the time we measure, sequential and quantitative. It is the time of appointments and deadlines, of physics equations and train schedules. Kairos is different. It is qualitative time, the right or opportune moment, time experienced rather than measured. A moment with a loved one that seems to stretch into eternity, or the perfect instant to speak a truth that has waited patiently to be voiced. These belong to Kairos. If time is not truly a river, what if, instead, it is more like a vast landscape, a terrain, where past, present, and future exist simultaneously, like different countries sharing the same continent? Einstein once suggested that the distinction between past, present, and future is only a stubbornly persistent illusion. Perhaps all moments exist together, like pages in a book, and our consciousness simply turns those pages one by one, creating the sensation of flowing time. This view of time as a landscape rather than a river has been called the block universe theory. In this conception, time does not flow. Rather, all of time, past, present, and future, exists at once in a four-dimensional block of spacetime. Our experience of the present moment moving forward is merely how our consciousness interacts with this eternal structure. Just as all locations in space exist simultaneously, even though we can only be in one place at a time. Perhaps all moments in time exist simultaneously, though we experience them sequentially. The poet T.S. Eliot captured something of this perspective when he wrote, "Time present and time past are both perhaps present in time future, and time future contained in time past." His words suggest a circularity, an eternal presence that transcends our linear experience. The mystics of many traditions have described similar insights, moments of clarity when the artificial boundaries between past, present, and future seem to dissolve, revealing a deeper unity beneath the apparent flow of time. Imagine sitting by a window early in the morning, cup of tea warming your hands, watching as the first light touches the world. The steam rises in delicate curls from your cup, catching the golden light. Perhaps it is raining softly, droplets tracing wandering paths down the glass, each following a unique trajectory determined by invisible variations in the surface. Or perhaps the day is clear, the sky gradually shifting from deep indigo to pale blue as the sun approaches the horizon. There is a certain peace in these moments when time seems to slow its persistent march. The dew glistens on grass and leaves, birds begin their gentle conversations, and the air holds a particular stillness that will soon dissolve as the day awakens fully. These quiet dawn moments have been experienced by countless humans across millennia. The shepherd watching his flock as the first light touches the hills, the monk rising for morning prayers, the insomniac who has watched the night hours pass and now finds solace in the day's rebirth. Though separated by time and culture and circumstance, their experience of this liminal moment connects them across the centuries. Perhaps this is another way in which time is not quite the rigid, linear progression we imagine it to be. Perhaps these shared human experiences create bridges across time's apparent boundaries. It is in quiet moments like these that we might ponder time's arrow, that mysterious quality that seems to push everything in one direction. We remember the past, but cannot see the future. Eggs can break, but never unbreak. Coffee cools, but never spontaneously reheats. A drop of cream in black coffee gradually disperses, spreading in beautiful, swirling patterns that never spontaneously reverse to reform the original droplet. This one-way direction, this arrow, points always toward increasing entropy, increasing disorder. It is fundamental to our experience of reality, so deeply ingrained that we rarely question it. The British astronomer Arthur Eddington first described this concept of time's arrow in 1927, identifying its connection to entropy, the measure of disorder in a system. The second law of thermodynamics tells us that in any closed system, entropy always increases over time. An ice cube melts in warm water. It never spontaneously reforms from the water. A book falls from a shelf and its pages scatter. They never reassemble themselves and leap back into place. Broken glass does not mend itself. These everyday observations reflect a profound asymmetry in how the physical world behaves over time. Yet, in the equations of physics, time's arrow is not always so clear. Many fundamental laws of nature work perfectly well whether time runs forward or backward. They are, as physicists say, time-symmetric. Newton's laws of motion, Maxwell's equations of electromagnetism, even the relativistic and quantum equations that govern the subatomic world, these remain valid if the direction of time is reversed. If you were to watch a film of two billiard balls colliding, you couldn't tell whether the film was playing forward or backward, because both directions obey the same physical laws. So why do we experience time in only one direction? Why does the arrow fly only one way? If the basic laws of physics don't distinguish between past and future, what creates the profound asymmetry we observe in everyday life? This question has puzzled scientists and philosophers for generations, and it remains at the heart of our understanding of time. Perhaps it is simply the nature of memory. We remember the past, but not the future. And so we perceive time as flowing in one direction. Our brains form neural pathways that encode experiences as they happen, creating a record that we can access later. We have no corresponding mechanism for accessing future events. This psychological arrow of time might be fundamental to our subjective experience. Even if the physical universe itself doesn't inherently distinguish between temporal directions, or perhaps time's arrow is connected to entropy itself, to the universe's gradual journey from order to disorder. In the early universe, matter was distributed with remarkable uniformity, but also extraordinary density and heat, a state of low entropy, but in a different form than we typically recognize. As the universe expanded and cooled, gravity drew matter together into stars and galaxies, creating local decreases in entropy, while the overall entropy of the universe continued to increase through other processes, particularly the distribution of energy as heat. This cosmological evolution may have established time's arrow at the grandest scale, with all other manifestations, from cooling coffee to aging bodies, simply reflecting this primordial asymmetry. The physicist Ludwig Boltzmann suggested in the 19th century that perhaps time's arrow is merely statistically reflection of the fact that disordered states are vastly more numerous than ordered ones. By this view, it's not impossible for an egg to unbreak or for heat to flow from cold to hot. It's just extraordinarily, unimaginably improbable. These questions have occupied philosophers and physicists for centuries, and they rest at the heart of any consideration of time travel. For if time is truly a landscape rather than a river, might it be possible to visit different regions of this terrain? Might we someday walk the pathways of the past or glimpse the vistas of the future? The answers depend in part on whether time's arrow represents a fundamental property of the universe, or merely a particular perspective on a more symmetric reality. As night deepens around us, perhaps you're growing more relaxed, your thoughts drifting like clouds across a summer sky. That's perfectly fine. Let these ideas about time flow through you without effort. There's no need to grasp at understanding. Sometimes the deepest insights come when we allow our analytical mind to rest, when we perceive patterns and connections intuitively rather than intellectually. Time itself seems to understand this principle. Its deepest secrets often reveal themselves in moments of quiet contemplation rather than active pursuit. In the early years of the 20th century, a patent clerk named Albert Einstein sat at his desk in Bern, Switzerland, and quietly revolutionized our understanding of time. The desk was ordinary wooden, functional, unremarkable. The room was modest. Outside, the streets of Bern would have been filled with the sounds of horses' hooves on cobblestones, the calls of street vendors, the conversations of passers-by going about their daily business, unaware that nearby the nature of reality itself was being reimagined. Einstein was just 26 years old in 1905, his now famous wild hair not yet white, his face still youthful. He worked long hours at the patent office, evaluating applications for new inventions with careful attention to detail. But in his free time, his mind explored territories far beyond the mechanical devices that crossed his desk. He pondered questions that had troubled physicists for decades: the nature of light, the structure of atoms, and most fundamentally, the character of space and time themselves. Within this unassuming space, time and space themselves were being rewoven into a single fabric, spacetime. Einstein's gentle revolution came not with dramatic proclamations or sudden insights, but through patient contemplation and mathematical exploration. There was no eureka moment, no apple falling from a tree, just the steady accumulation of thought upon thought, equation upon equation, insight upon insight. His special theory of relativity, published in 1905, revealed that time is not absolute. It does not tick at the same rate for everyone, everywhere. Instead, time's flow depends on relative motion and gravity. Two identical clocks will measure time differently if one is moving relative to the other, or if one experiences stronger gravity. This was not merely a mathematical curiosity, it was a fundamental reimagining of reality itself. The implications were profound. Before Einstein, physicists had followed Newton in treating time as an absolute universal flow, identical for all observers, regardless of their state of motion. Minutes and seconds were thought to pass at the same rate for everyone, everywhere in the universe, like a cosmic metronome beating out identical intervals across infinite space. Einstein showed that this comforting picture was an illusion, that time itself is relative, flexible, dependent on the observer's frame of reference. Imagine two friends sitting in separate rooms, each with an identical clock. From their individual perspectives, time passes normally. The second hand sweeps around the clock face at the expected rate. Their hearts beat at their usual rhythm. Their thoughts flow at their accustomed pace. But if one room were somehow accelerated to near light speed, or placed near a massive gravitational source like a black hole, something remarkable would happen. While each person would experience time normally within their own reference frame, an outside observer would see dramatic differences between the two clocks. From the outside perspective, time would pass more slowly in the moving room or the room, experiencing stronger gravity. The clock in that room would tick more slowly. The heart of its occupant would beat more slowly. Even the thoughts of that person would unfold more gradually, though they themselves would notice no difference. This effect, called time dilation, is not a perceptual illusion or a problem with the clocks. It is a fundamental property of time itself. These effects are not noticeable in our everyday lives because we never approach the speed of light. And Earth's gravity, while sufficient to keep us grounded, is relatively weak in cosmic terms. The differences in time's flow that we might experience moving at highway speeds or climbing a mountain are so minute that only the most sensitive atomic clocks can detect them. But these effects have been measured with such clocks. They are real. Time itself is malleable. In one famous experiment conducted in 1971, physicists Joseph Haffel and Richard Keating placed atomic clocks aboard commercial airliners and flew them around the world, then compared their time measurements with identical clocks that had remained on the ground. The airborne clocks recorded slightly different elapsed times than their earthbound counterparts, precisely as Einstein's theories predicted. Similar experiments using even more precise clocks have confirmed these results repeatedly. The GPS system in your phone or car relies on these relativistic corrections. Without them, location errors would accumulate at a rate of about 10 kilometers per day. Einstein expanded on these insights 10 years later with his general theory of relativity, which described gravity not as a force but as a curvature of spacetime itself. Massive objects like stars and planets create dips in this fabric, like heavy balls placed on a stretched rubber sheet. Other objects follow these curves, and we perceive this motion as the effect of gravity. A planet orbits its star not because an invisible force pulls it into a closed path, but because it follows the curved path of spacetime created by the star's mass. This elegant theory not only explained gravity more accurately than Newton's work had, but it also opened theoretical doors to concepts that once seemed purely in the realm of science fiction, including the possibility of time travel. If space and time form a unified fabric that can be curved and stretched by mass and energy, might it be possible to create a path through this fabric that returns to an earlier point? Might the curves be shaped in ways that allow movement not just through space, but also through time? The mathematics of general relativity suggest that such paths, called closed timelike curves, can exist under certain conditions. These theoretical possibilities emerge not from wild speculation, but from the same equations that accurately predict the bending of starlight around the Sun, the precise orbit of Mercury, and the existence of black holes. The same mathematical framework that has been confirmed by countless observations also contains these strange potential doorways through time as evening settles around us. Imagine sitting in a room with an old grandfather clock. Its pendulum swings with hypnotic regularity, marking seconds that can never be reclaimed. The warm lamplight catches dust motes floating in still air. The wood of the clock's case gleams softly, polished by years of careful attention. The brass mechanism inside ticks with precise movements, each gear and lever performing its appointed task in an intricate mechanical dance that translates the falling energy of a weight into the measured passing of time. The clock face, with its ornate hands and delicately painted numerals, presents time as something we can see and measure, something we can hold within the comfortable boundaries of minutes and hours. It is in this peaceful setting that we might contemplate one of the most troubling aspects of time travel, the paradoxes. The most famous of these is perhaps the grandfather paradox. Imagine traveling back in time and, through some accident or intention, preventing your grandfather from meeting your grandmother. This would mean your parent would never be born, and, consequently, neither would you. But if you were never born, how could you travel back in time to prevent your grandparents meeting? The paradox creates a logical loop with no resolution, a story that contradicts itself. The grandfather paradox is disturbing because it violates our deep intuition about causality, the principle that causes must precede their effects, that the arrow of time points in only one direction. In our everyday experience, events flow logically from past to future. The past influences the present, which in turn shapes the future. We can affect the future through our actions, but the past seems fixed, unchangeable, a closed book. Time travel to the past would seemingly allow effects to precede their causes, creating logical impossibilities that challenge our understanding of reality itself. There are variations of this paradox. The bootstrap paradox, for instance, questions the origin of information or objects in a time loop. Imagine a scientist who receives the designs for a time machine from her future self. She builds the machine and, years later, uses it to travel back and give the designs to her younger self. But where did the designs originally come from? They exist in a closed temporal loop with no clear point of origin, no moment of original creation. The information seems to bootstrap itself into existence, appearing from nowhere. Consider a simpler example. A musician travels back in time and plays a beautiful melody for his childhood hero, who is so impressed that he incorporates it into his work. This music eventually inspires the time traveler, who learns it as a child, but who composed the melody. It seems to exist in a loop with no beginning, no moment of creation. Information has been created from nothing, violating our understanding of causality. These paradoxes have led some theorists to suggest that time travel to the past must be impossible, that some law of physics must prevent it to preserve causality, the principle that causes must precede their effects. Perhaps the universe has built-in protections against such logical contradictions. Fundamental laws that prohibit closed timelike curves or prevent them from being traversable. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel and thus protect the ordering of cause and effect. Yet other physicists have proposed solutions to these paradoxes. Perhaps time travel creates parallel timelines or alternate realities. So the traveler's actions in the past create a new branch of history rather than changing the traveler's own past. In this view, a time traveler who prevents his grandparents from meeting doesn't erase himself from existence. Rather, he creates a new timeline in which his counterpart will never be born, while he himself continues to exist, having originated from the original timeline where his grandparents did meet. This solution, sometimes called the many worlds interpretation, avoids logical contradictions by multiplying realities. Or perhaps the universe somehow conspires to prevent paradoxes, a principle that Russian physicist Igor Nevikov called the self-consistency principle. According to this view, you could try to change the past, but something would always prevent you from creating a paradox. You might slip on a banana peel just as you were about to prevent your grandparents meeting. Or your interference might actually be the very thing that caused them to meet in the first place. The universe maintains its internal consistency by ensuring that all events, even those involving time travelers, form a coherent, non-contradictory whole. This principle suggests that free will might be more constrained than we typically imagine. A time traveler attempting to change the past would find that circumstances conspire to prevent any change that would create a paradox. This doesn't mean the traveler has no free will, but rather that the range of possible actions is limited to those consistent with what we know has already happened. The past, present, and future must form a coherent whole, without logical contradictions. Whether these paradoxes truly represent logical impossibilities or merely violations of our intuitions about how causality should work. In a block universe where all of time exists simultaneously, perhaps causality is more complex than our linear experience suggests. Perhaps effects can sometimes precede their causes without creating true contradictions, just as a circle has no beginning or end, but remains a logically coherent shape. as the grandfather clock continues its measured ticking. Each swing of the pendulum marking another second passing into history. We might reflect on how these abstract paradoxes touch on deep questions about the nature of reality, free will, and the structure of time itself. They are not merely intellectual puzzles, but windows into the fundamental architecture of our universe. These philosophical puzzles aside, what physical mechanisms might theoretically allow time travel? Einstein's equations suggest several possibilities, doorways through spacetime that might permit journeys to the past or future. These theoretical constructs emerge not from wishful thinking, but from the mathematics of general relativity, the same mathematics that has successfully predicted phenomena later confirmed by observation, from the bending of starlight to the existence of gravitational waves, wormholes, tunnels, connecting distant regions of spacetime. One such theoretical possibility, first proposed by physicist Ludwig Flamm in 1916 and later explored by Albert Einstein and Nathan Rosen. Wormholes represent shortcuts through spacetime. Imagine spacetime as a sheet of paper. Normally, to get from one point to another, you must travel across the paper's surface. But if you fold the paper so that 2 points touch, you could create a shortcut, a wormhole, allowing almost instantaneous passage between locations that might otherwise be separated by vast distances. The mathematics of general relativity permit such structures, at least in theory. A wormhole would have 2 mouths connected by a throat, creating a tunnel through a higher dimension. Matter entering one mouth would emerge from the other, having traversed the throat rather than the longer path through normal spacetime. If the 2 mouths were located in the same spatial position, but at different times, the wormhole would function as a time machine, allowing travel into the past or future. However, natural wormholes, if they exist at all, would likely be microscopic and unstable, collapsing instantly if any matter attempted to pass through them. Creating a traversable wormhole would require exotic forms of matter with negative energy density, matter that weighs less than nothing, pushing outward rather than pulling inward with its gravity. While quantum mechanics suggests that such negative energy states might exist in limited forms, the Casimir effect demonstrates this in a restricted context. It remains unclear whether sufficient quantities could ever be harnessed to stabilize a macroscopic wormhole. In theory, a sufficiently advanced civilization might be able to create and stabilize such structures, perhaps using exotic forms of matter with negative energy density. A properly configured wormhole might connect not just different places but different times, allowing passage to the past or future. The physicist Kip Thorne, who consulted on the film Interstellar, has explored the theoretical requirements for such time-traversing wormholes in his scientific work. Another theoretical possibility involves cosmic strings, hypothetical defects in space-time left over from the early universe. These incredibly thin, incredibly dense objects would stretch across vast distances, warping spacetime around them. 2 cosmic strings, moving past each other at high speeds, might, in theory, create closed timelike curves, paths through spacetime that return to their starting point in time as well as space. A spaceship flying around such an arrangement in the right way might find itself returning to its own past. Cosmic strings, if they exist, would be unimaginably thin, narrower than a proton, but enormously dense, with a mass of perhaps 1,022 grams per centimeter of length. They would warp the surrounding spacetime, creating a deficit angular geometric distortion where a circle drawn around the string would have a circumference less than 2 pi times its radius. While cosmic strings themselves are highly speculative, they emerge naturally from certain theories in particle physics and cosmology, and researchers continue to search for observational evidence of their existence. Massive rotating objects offer yet another possibility. In 1949, mathematician Kurt Gödel discovered that Einstein's equations permit a rotating universe to contain closed timelike curves, potentially allowing time travel. While our universe as a whole does not appear to rotate, the same mathematics might apply to local regions of spacetime affected by extremely massive rotating objects like black holes. A very massive, rapidly rotating cylinder, sometimes called a Tipler cylinder, after physicist Frank Tipler, who studied such objects, might create a frame-dragging effect strong enough to form closed time-like curves in the surrounding spacetime. The mathematics of these solutions are complex, involving tensor calculus and differential geometry, fields that lie at the frontier of modern theoretical physics. Yet there is a certain beauty in the quiet patterns they reveal, the whispering mathematics of closed time-like curves, even if we never succeed in building a time machine. These theoretical explorations reveal the rich structure of spacetime itself, the hidden geometries that shape our reality in ways our everyday experience rarely suggests. A closed time-like curve is simply a path through spacetime that returns to its starting point in time. Imagine a circle drawn on paper. If you follow the circle, you eventually return to where you started. A closed time-like curve is similar, except the circle includes movement through time as well as space. According to general relativity, such paths can exist in certain space-time geometries. They would allow an object to return to its own past journey through time. The mathematics describing these curves are elegant, written in the language of tensors and differential geometry. They emerge naturally from Einstein's field equations. Under certain conditions, like solutions to a complex puzzle that was hidden within the mathematics all along. These equations don't tell us whether such curves can actually exist in our universe, but they show that they are compatible with our best understanding of how gravity shapes spacetime. Consider the Kerr solution to Einstein's field equations, which describes the spacetime around a rotating black hole. For a black hole rotating rapidly enough, the mathematics predicts a region called the ergosphere, where spacetime itself is dragged along with the black hole's rotation. Beyond this lies the event horizon, and inside that, under certain conditions, closed time-like curves might exist. An object following such a curve would find itself returning to its starting point in time, effectively traveling into its own past. These mathematical possibilities raise profound questions. If the laws of physics permit time travel, why haven't we encountered time travelers from the future? This question, first posed formally by physicist Enrico Fermi in the context of extraterrestrial life, the famous Fermi paradox, applies equally well to time travelers. If future civilizations develop time travel, shouldn't we see evidence of their visits to our era? Perhaps time travel to the past is physically possible, but practically unachievable, requiring energy sources or technologies beyond what any civilization could reasonably develop. Or perhaps time travel is possible, but can only reach times after the creation of the first time machine, explaining why we haven't encountered travelers from the future. They can't reach us because we haven't yet built the receiver for their temporal journeys. Asterisk. Or perhaps time travelers are here, but carefully conceal their presence, observing our era without interfering in ways that would reveal their existence. This scenario appears in many works of fiction, from Star Trek to Doctor Who, where time travelers follow non-interference directives to prevent disruption of the timeline. If such travelers exist, their success would be measured by their invisibility. The perfect time traveler would leave no trace of their journey. Yet even as these theoretical doors to time travel stand slightly ajar in the equations of general relativity, other aspects of physics seem determined to close them. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow conspire to prevent time travel and thus protect chronology, the normal ordering of cause and effect. Without such protection, the logical paradoxes of time travel might unravel the fabric of reality itself. Hawking suggested that quantum effects would likely destabilize any attempt to create a time machine, preventing closed timelike curves from forming. The universe, it seems, might be its own quiet guardian against the paradoxes of time travel. When physicists analyze what might happen near a wormhole or other potential time machine, they find that energy tends to build up at the threshold of a closed timelike curve. This energy grows without bound as the time machine is about to form, potentially destroying the time machine before it can function. It's as though the universe itself enforces causality, preventing effects from preceding their causes. This enforcement happens not through any conscious agency, but through the quiet interplay of physical laws, gravity, quantum mechanics, thermodynamics working together to maintain the familiar flow of time from past to future. The mechanisms are subtle, arising from the complex interaction of fields and forces at the quantum level, but their effect may be profound. A universe that permits the mathematics of time travel, while simultaneously ensuring that such journeys remain forever theoretical. Yet even without traversable wormholes or cosmic strings, we already observe a kind of natural time travel in our universe through the phenomenon of time dilation. A patient observer might note that time does not pass at the same rate for everyone. According to special relativity, a clock in motion relative to an observer will appear to tick more slowly than a stationary clock. This effect, called time dilation, has been confirmed by experiments with precise atomic clocks. Similarly, general relativity predicts that clocks in stronger gravitational fields will tick more slowly than clocks in weaker fields. Imagine two identical atomic clocks, precise to the nanosecond. One remains on Earth, while the other is placed aboard a spacecraft traveling at a significant fraction of the speed of light. When the traveling clock returns to Earth, it will have recorded less elapsed time than the stationary clock. The difference is not due to any mechanical failure or environmental factor. It reflects a fundamental property of time itself. The The traveling clock hasn't just measured time differently. It has experienced time differently. This isn't merely theoretically, it has been confirmed experimentally. First with atomic clocks on airplanes, and later with increasingly precise measurements using atomic clocks and high-speed particles. Similarly, a clock at sea level will tick slightly more slowly than an identical clock on a mountaintop, because the sea level clock experiences stronger gravity. The effect is minuscule. At such scales, a clock on Mount Everest would gain about 30 microseconds per year compared to an identical clock at sea level. But it is real and measurable with modern atomic clocks. These effects are happening all around us, though usually at scales too small for human perception. Astronauts on the International Space Station, orbiting at 17,500 miles per hour and experiencing slightly weaker gravity than we do on Earth's surface, age about 0.01 seconds less per year than they would on Earth. Over a 6-month mission, an astronaut experiences about 0.005 seconds less time than those of us on the ground. The record holder is cosmonaut Gennady Padalka, who has spent 879 days in space across multiple missions, experiencing about 0.02 seconds less time than he would have on Earth, making him, in a very real sense, a time traveler who has journeyed about 20 milliseconds into the future relative to Earth. GPS satellites must account for both special and general relativistic time dilation to maintain their accuracy. The satellites orbit at about 14,000 kilometers above Earth's surface, where gravity is weaker than on the ground, causing their clocks to tick faster by about 45 microseconds per day. However, their orbital speed of 14,000 kilometers per hour causes their clocks to tick more slowly by about 7 microseconds per day due to special relativistic time dilation. The net effect is that the satellite clocks run about 38 microseconds faster each day than ground-based clocks. Without correcting for this difference, GPS positions would drift by about 10 kilometers per day due to the slight differences in how time flows for the satellites compared to Earth's surface in more extreme conditions. Time dilation becomes more pronounced near a black hole, where gravity is extraordinarily strong. Time can slow dramatically relative to distant observers. A clock placed near a black hole's event horizon might tick only once for every 1,000 or million ticks of a distant clock. An astronaut who spent time near such a horizon and then returned to Earth might find that while only a few years had passed for them, centuries had elapsed on Earth. They would have effectively traveled into Earth's future, though they themselves would have experienced time normally throughout their journey. This scenario was depicted in the film Interstellar, where astronauts visiting a planet near a massive black hole experience severe time dilation. Every hour on the planet corresponds to 7 years passing on Earth. While the specific numbers in the film were chosen for dramatic effect, the underlying physics is sound. Near massive objects, time really does slow down relative to more distant observers. This is not merely theoretical. We observe evidence of extreme time dilation in the radiation from matter orbiting close to black holes, where the orbital periods and energy signatures match predictions from general relativity. So, in a very real sense, time travel to the future is not only possible, but has been experimentally verified. The challenge lies in the scale. Human technology cannot yet accelerate a person to speeds where time dilation becomes significant on human timescales. Nor can we safely approach black holes or other extreme gravitational fields. And importantly, these natural forms of time dilation only allow one-way journeys to the future. They offer no path back to the past. Nevertheless, they remind us that time is not the rigid, universal flow we intuitively perceive. It stretches and compresses according to motion and gravity, creating subtle variations in its passage, variations that hint at deeper possibilities as the night deepens around us. Perhaps your thoughts are growing more diffuse, your awareness softening at the edges. That's perfectly natural. Let yourself drift with these ideas about time and its mysteries. There's no need to hold tightly to each concept. Rather, allow them to wash over you like gentle waves on a shore. Time itself has many textures, sometimes flowing quickly, sometimes lingering in moments of perfect stillness. Tonight, we explore its quieter currents, the slow eddies and peaceful pools where wonder gathers, as we continue our gentle exploration of time and its travelers. Let us turn to some curious findings that have puzzled archaeologists and historians, artifacts that seem out of place in time. These whispers from the past sometimes tell stories that don't quite align with our understanding of history, raising quiet questions about the linearity of time or the possibility of anachronistic knowledge. The ancient world occasionally yields objects that seem to anticipate technologies or knowledge from much later periods. These out-of-place artifacts, uparts, as some researchers call them, challenge conventional historical narratives. While most can be explained through careful analysis, they remind us that the path of human innovation is rarely as straightforward as textbooks might suggest. Consider the Antikythera mechanism, discovered in 1901 in a shipwreck off the Greek island of Antikythera. This ancient device, dating to around 100 BCE, contains an intricate system of at least 30 bronze gears that model the movements of the sun, moon, and planets with remarkable precision. When first discovered, broken into dozens of corroded fragments, it appeared to be little more than a curious lump of bronze and wood. Only decades later, as imaging technology improved, did researchers begin to appreciate its true complexity. X-ray analysis revealed that the mechanism could predict astronomical positions, solar and lunar eclipses, and even the irregular orbit of the moon with extraordinary accuracy. Its sophistication and precision were not matched until the development of astronomical clocks in medieval Europe. Over 1,000 years later, it could track the Metonic cycle, the Saros cycle, and other complex astronomical periods known to ancient astronomers, but rarely, if ever, mechanized before the Renaissance. How did ancient Greek astronomers and craftsmen create such a device? The conventional explanation involves the gradual accumulation of astronomical knowledge and mechanical expertise throughout the Hellenistic period, culminating in this remarkable calculator. We know that Greek mathematicians like Archimedes designed complex mechanical devices, though none have survived intact. The mechanism's solitary sophistication remains striking, however. It stands alone, without clear predecessors or contemporaries of similar complexity. It is as though a single laptop computer were discovered in a context where all other technology was at the level of simple mechanical calculators. Or consider the Baghdad Batteria clay jar containing a copper cylinder and iron rod discovered in Iraq and dating to the Parthian period around 250 BCE to 224 CE. When filled with an acidic liquid like vinegar, the device can produce a small electric current, while conventional explanations suggest it may have been used for electroplating or medicinal purposes. Its existence raises questions about ancient understanding of electricity. Long before modern electrical theory developed in the 18th and 19th centuries, experiments with replicas have shown that such devices could produce voltages between 0.8 and 2 volts, enough for simple electroplating of silver onto copper, or perhaps for certain medical treatments involving mild electrical stimulation. Some researchers have suggested that multiple batteries might have been connected in series to produce higher voltages. Ancient texts, however, make no clear reference to electrical phenomena being harnessed in these ways, leaving the true purpose of these devices uncertain. The Quimbaya artifacts from Colombia, dating to around 1000 CE, include small gold objects that resemble modern aircraft, with delta wings, stabilizing tails, and even what appear to be propellers in some cases. While conventional archaeological interpretation identifies these as stylized representations of birds, insects, or fish, their aircraft-like appearance has led some to suggest they might represent flying devices unknown to conventional history. Similar controversies surround ancient Egyptian hieroglyphs at the Temple of Seti I in Abydos, which appeared to depict helicopters and other modern vehicles, though mainstream Egyptologists explain these as the result of overlapping symbols from different time periods created through the recarving of earlier inscriptions. These and other artifacts do not necessarily indicate time travel or intervention from the future. Archaeological contexts are complex, and human ingenuity often surpasses our expectations. Many seemingly anachronistic artifacts have conventional explanations involving lost technologies, independent invention, or misinterpretation of the evidence. Yet they remind us that history is not always as linear or progressive as we might assume. Knowledge can be gained and lost. Technologies can emerge and then fade away, only to be rediscovered centuries later. The path of human development contains many quiet diversions and unexpected turns. The ancient Greeks understood the principle of the steam engine. Hero of Alexandria designed a primitive steam-powered device called an iolopile in the 1st century CE, but never applied it to practical transportation or industrial purposes. The Chinese invented gunpowder, but initially used it primarily for fireworks rather than weapons. The Mayans developed sophisticated mathematics and astronomy, but never used the wheel for transportation, despite including it in children's toys. These historical curiosities suggest that technological development depends not just on knowledge but on social context, economic incentives, and cultural frameworks that determine which innovations are pursued and which remain curiosities. Perhaps most intriguing are ancient texts that seem to describe technologies or concepts far ahead of their time. The Samarangana Sutradhara, an 11th century Sanskrit text, contains passages that some interpret as describing flying machines. Strong and durable must the body be made, like a great flying bird of light material. Inside it, one must place the Mercury engine with its iron heating apparatus beneath, by means of the power latent in the Mercury, which sets the driving whirlwind in motion. A man sitting inside may travel a great distance in the sky in a most marvelous manner. The ancient Indian epic Mahabharata includes descriptions of weapons with destructive power reminiscent of modern nuclear weapons. A single projectile charged with all the power of the universe, an incandescent column of smoke and flame as bright as 10,000 suns rose in all its splendor. It was an unknown weapon, an iron thunderbolt, a gigantic messenger of death, which reduced to ashes the entire race of the Vrishnis and the Andakas. These texts most likely represent mythological or poetic expressions rather than literal descriptions of advanced technology. Many cultures have creation myths and legendary weapons of immense power, from Thor's hammer to Zeus's thunderbolts. Yet they spark the imagination and raise gentle questions about the origins of such ideas in pre-industrial societies. How did ancient poets conceive of weapons that could destroy entire cities in a flash of light? What inspired visions of flying machines in cultures that had never seen powered flight? As we ponder these archaeological whispers, it's worth noting that the absence of evidence is not evidence of absence. If future time travelers were to visit the past or present or earlier times, they might take great care not to leave traces of their presence, especially technological artifacts that could alter the course of development. Perhaps the most successful time travelers would be those whose journeys remained completely undetected, leaving no footprints across the sands of time. Or perhaps what evidence they do leave behind is misinterpreted, categorized as anomalous, but not impossible within conventional historical frameworks. Modern archaeological techniques grow more sophisticated each year. Ground-penetrating radar, LiDAR mapping, isotope analysis, ancient DNA sequencing, and other advanced methods are revealing aspects of the past invisible to earlier generations of researchers. Perhaps these tools will eventually resolve the mysteries surrounding out-of-place artifacts, either by confirming conventional explanations or by revealing new insights that change our understanding of historical, technological development. Or perhaps some mysteries will remain, persistent whispers suggesting that time's flow might be more complex than our linear models indicate. Expanded text, time travelers among austenite. We drift together into a gentle exploration of time itself, and those who might traverse its mysterious currents. You don't need to follow every word or concept, just let these thoughts flow around you like water over smooth stones. Perhaps you're lying down, eyes growing heavy, or simply seeking a quiet moment of wonder. However you've arrived here, know that this space is yours to experience in whatever way brings you peace. Time, after all, is patient. It will wait for us as we move through this journey together. As you settle in, feel the weight of your body against the surface supporting you. Notice the texture of fabric against your skin, the subtle sounds of your environment, perhaps the distant hum of electronics, the gentle whisper of your own breath, or the soft ticking of a clock marking time's passage. These sensations anchor you in the present moment, even as we prepare to explore the vast territories of time together. Take a slow, deep breath, allowing your chest to rise and fall at its own natural pace. Time exists in this breath, in the inhale that becomes an exhale, in the continuous cycle of renewal that has accompanied you since your first moments in this world. The night deepens around us as we begin our journey. Perhaps stars are visible through your window, their light having traveled for years, decades, or even centuries before reaching your eyes. Natural time travelers in their own right, messengers from the distant past, still visible in our present. Or perhaps your space is illuminated only by the soft glow of artificial light, a technology that would have seemed magical to those who lived just a few centuries ago. We exist in a particular moment in time's vast expanse, surrounded by echoes of the past and seeds of the future, connected to all who have come before and all who will follow through the invisible threads of temporal continuity. Language surrounds us like an invisible ocean, its currents constantly shifting, its tides rising and falling across generations. We swim in this ocean without often noticing its movements, the subtle changes in vocabulary, pronunciation, grammar, and meaning that occur between one year and the next, one decade and the next, one century and the next. These linguistic transformations happen gradually enough that we rarely perceive them in real time. Yet, when we look back across history, we find ourselves confronted with versions of English that would sound almost foreign to our modern ears. Consider the opening lines of Chaucer's Canterbury Tales, written in the late 14th century. One that April with his showers soot, the drought of marsh hath pursed to the root. To modern readers, this Middle English requires translation, yet it represents the same language we speak today, separated from us by just 20 generations. The distance between Chaucer's English and our own illuminates the constant evolution of language, a process that continues even now, though perhaps more subtly in our age of recorded sound and global communication. Even basic pronunciation changes over time. The great vowel shift that occurred in English between 1400 and 1700 transformed the very sound of the language. Before this shift, the word time was pronounced something like team. Mouse sounded closer to moose, and house resembled hoose. This wasn't a minor variation in accent, but a fundamental reorganization of English. Vowel sounds that swept gradually across regions and social classes, eventually creating the pronunciation patterns we now consider standard. If you were to travel back to Shakespeare's London and listen to a performance at the Globe Theatre, you might be surprised by how different the pronunciation would sound from modern performances of the same plays. The R sounds would be more strongly pronounced. Certain vowels would have qualities unfamiliar to our ears, and the rhythm and cadence of speech would strike us as notably different from contemporary English. Yet the audiences of the time perceived nothing unusual. They were simply speaking their language as they always had, unaware that future generations would pronounce the same words quite differently. This remarkable transformation didn't happen suddenly. No one woke up one morning speaking differently. Rather, it unfolded over generations, with each subtle shift barely noticeable to those living through it. Children would pronounce certain words slightly differently from their parents. These small changes accumulating and spreading until, over 3 centuries, the entire sound system of English had been transformed. What's fascinating is that people at the time were largely unaware of this massive linguistic change happening around and within them. We can trace this pattern through literary works. Chaucer's Canterbury Tales, written in the late 14th century, contains rhymes that only make sense if we pronounce the words as they were spoken before the great vowel shift. When Chaucer rhymed grace with space, both would have been pronounced with an ah sound rather than the long a we use today. By Shakespeare's time in the late 16th and early 17th centuries, the shift was well underway but not complete, creating an interesting transitional form of English pronunciation that would sound peculiar to our modern ears, while changes happen more slowly in our media-saturated age. They continue nonetheless. The standardization of pronunciation through radio, television, and now internet media has somewhat slowed the pace of change, but it hasn't stopped it. New sounds enter the language through borrowed words, slang, and innovative pronunciations. The vocal fry, a creaky, low-pitched vibration at the end of words, emerged as a speech pattern among young American women in the early 21st century and has gradually spread to other demographic groups. The uptalk pattern, ending statements with a rising intonation that makes them sound like questions, similarly spread through English-speaking countries over recent decades. Listen to recordings from just 50 years ago's broadcasts, interviews, films, and you'll notice subtle differences in pronunciation, cadence, and vocal quality. The formal, somewhat clipped pronunciation style of mid-20th century American broadcasting sounds distinctly dated to contemporary ears. Go back further to recordings from the 1920s or 1930s, and the differences become even more pronounced. The accent known as transatlantic or mid-Atlantic, an artificial hybrid of American and British pronunciation taught in elite schools and used in early Hollywood films, has vanished almost entirely, though it was once considered the standard for educated American speech. These contemporary changes are subtle enough that many people don't notice them consciously, yet distinctive enough that recordings from just 50 years ago often sound dated to our ears. News broadcasts from the 1950s feature a clipped, formal pronunciation style that few speakers use today. Recordings from the 1920s reveal even more dramatic differences in rhythm, emphasis, and vowel qualities. Though we might understand the words, the overall sound strikes us as distinctly old-fashioned. Regional accents grow more or less pronounced over time, responding to patterns of migration, education, and media influence. Some distinctive regional dialects in the United States have weakened as populations became more mobile and exposed to standardized media pronunciations. Yet, simultaneously, other regional features have persisted or even strengthened as markers of local identity and authenticity. The Southern drawl, the New York accent, the distinctive patterns of speech in Boston or Minnesota, all continue to evolve rather than simply disappearing into a homogenized national standard. In certain isolated communities, linguistic evolution follows unique paths. The dialect of English spoken on Tangier Island in Chesapeake Bay preserves features from early modern English that have disappeared elsewhere, creating a speech pattern that sounds to outsiders like a strange mixture of Elizabethan English and Southern American dialect. Similarly, the English spoken in parts of Appalachia retains words and grammatical structures from the 18th century Scots-Irish settlers, preserved through geographical isolation. These linguistic time capsules remind us that language evolution doesn't follow a single path, but branches and diversifies according to the specific historical and social conditions of each community. Global influences introduce new phonetic elements. As English spreads worldwide and absorbs features from other languages, the rhythm and melodic qualities of Indian English, the distinctive consonant patterns of Korean English, the vowel systems of Nigerian or Singaporean English, all these variations contribute to an increasingly diverse global language. What we call English is becoming a family of related dialects, each with its own pronunciation patterns, vocabulary innovations, and grammatical particularities. Consider how the simple greeting hello might be pronounced differently across the English-speaking world, with different vowel qualities, varying emphasis patterns, distinct melodic contours. These variations aren't random, but follow systematic patterns influenced by the native languages of speakers in different regions, the historical pathways through which English spread, and the local linguistic environments in which English has evolved. A form of English spoken nowhere today might emerge in the future, combining elements from existing varieties in new and unpredictable ways. Generational differences create distinct speech patterns that can serve as temporal markers. Each generation develops its own linguistic innovations, often as expressions of identity. The clipped mid-century cadences of the greatest generation, the relaxed vowels and questioning intonations of Generation X, the rapid delivery and vocal variations of millennials. These speech patterns become timestamps, placing speakers within particular eras. You might notice these generational markers in your own family. Perhaps grandparents pronounce certain words differently than parents, who in turn differ from their children. Words like root, either, schedule, or controversy often revealed generational and regional differences in pronunciation. Even the way laughter is expressed textually has evolved from ha-ha to lol to younger generations using skis or simply keyboard smashing to indicate amusement. These markers may seem trivial, but they form part of the complex tapestry of linguistic evolution, containing subtle information about when and where a speaker acquired their language patterns. These ongoing transformations in pronunciation raise an intriguing possibility about time travelers. A visitor from the future might speak with an accent that doesn't quite match any contemporary regional dialect, perhaps combining elements that, to our ears, should not go together. Their speech might feature vowel shifts that haven't yet occurred in our time, consonant patterns that haven't yet emerged, or rhythmic elements that our current linguistic landscape doesn't include. Imagine someone speaking English with perfect grammatical fluency, yet pronouncing certain vowels in ways that sound off to us, not identifiable as any known accent from around the world, but somehow coherent within their own speech pattern. Perhaps certain diphthongs might be flattened, or traditionally, separate vowel sounds might be merged in ways that haven't yet occurred in our linguistic timeline. The sound might be simplified to T or D, a change already beginning in some urban dialects. Or perhaps our sounds might be pronounced with a particular vibration our ears can't quite place. Such a speaker might claim to be from an obscure region, or to have grown up in an isolated community with its own dialect. They might attribute their unusual pronunciation to having learned English through unusual circumstances. But to a trained linguist, their speech might contain patterns that are not simply unusual, but linguistically innovative, in ways that follow the internal logic of language evolution, suggesting not a random idiosyncrasy, but a coherent future development of English pronunciation. As you rest and listen to these thoughts about language's quiet transformations, imagine the English of 200 years from now. What sounds might change, which distinctions might fade, what new phonetic elements might enter the language through technology, cultural exchange, or the natural drift of human speech. The answers lie not in random chance, but in the patterns of change already underway, the subtle shifts that will accumulate generation by generation, until they create a version of English that would sound distinctly futuristic to our ears. Grammar and syntax also evolve across time, often in ways even more subtle than pronunciation changes. The progressive decline of the subjunctive mood in English, if I were becoming, if I was frequent. This shift has been underway for centuries, with the subjunctive gradually retreating from everyday usage, while maintaining a foothold in certain formal contexts and fixed expressions. For many younger speakers today, if I was you sounds perfectly natural, while the technically correct if I were you might sound overly formal or affected. This grammatical evolution follows a pattern we see repeatedly in language history: the simplification of complex inflectional systems. Old English, like its Germanic cousins, had an extensive case system with different forms for nouns, depending on their function in a sentence. By the time of Middle English, this system had largely collapsed, with word order taking over the grammatical function that case endings once served. The subjunctive represents one of the last vestiges of this older, more heavily inflected system, and its gradual disappearance continues this long-term trend toward simplification. The shifting use of prepositions offers another window into grammatical change happening around us. Phrases like different than instead of different from, wait on instead of wait for, or bored of instead of bored, with represent subtle shifts in prepositional usage that often begin as regional variations, before potentially becoming standard. These changes rarely affect meaning. Context makes the intended relationship clear, but they create distinctive patterns that mark specific periods in linguistic history. Consider how older generations might say, "I'm going to hospital," while younger speakers typically say, "I'm going to the hospital," or how British English and American English differ in prepositional usage, with phrases like at the weekend versus on the weekend. These variations aren't simply random differences, but represent systematic shifts that continue to unfold gradually across time and space. Streamlining of certain grammatical constructions represents another ongoing change: the gradual disappearance of whom in favor of who in all contexts, the declining use of the possessive apostrophe in certain constructions, the simplification of complex verb forms. All these represent the natural evolution of grammar toward efficiency, though prescriptivists might view them as deterioration rather than change. We can observe this streamlining in the declining use of the apostrophe in brand names and signs Starbucks coffee rather than Starbucks coffee, in the increasing acceptance of split infinitives to boldly go, and in the growing preference for simpler verb forms, I learned rather than I learned. These changes don't happen overnight, but accumulate gradually as speakers unconsciously prioritize ease of expression over traditional forms that may have become cumbersome or unnecessary for clear communication. These grammatical shifts, like pronunciation changes, happen gradually enough that we rarely notice them in progress. A construction that sounds slightly odd to older generations might sound completely natural to younger speakers. Rules that were once taught as absolute give way to new patterns through a process of gradual acceptance. What begins as an error eventually becomes an acceptable variant, and finally may become the new standard, with the older form eventually sounding archaic or overly formal. A time traveler navigating our era would face a particular challenge with these grammatical shifts. While vocabulary can be memorized and pronunciation can be practiced, the underlying patterns of grammar are often internalized at a deep level, making them harder to consciously monitor and control. A visitor from the future might use grammatical constructions that sound slightly formal or archaic to our ears, reflecting their study of earlier forms of English rather than natural acquisition. Or they might employ structures that haven't yet become commonplace in our time, perhaps using prepositions in innovative ways, simplifying certain verb constructions that we still maintain, or introducing new patterns of negation or question formation. Imagine someone who consistently uses shall where contemporary English uses will, or who employs the present perfect tense in contexts where modern American English would use the simple past. I have seen that movie last week, rather than I saw that movie last week. Such patterns might be dismissed as the quirks of a non-native speaker, but they could also represent the grammatical patterns of future English, where certain distinctions we maintain have disappeared or new ones have emerged. The temporal marker might be especially apparent in conditional constructions, which often evolve over time. A future form of English might handle counterfactuals differently, perhaps developing new modal verbs or particles to express degrees of possibility that our current grammar doesn't distinguish. A time traveler might inadvertently use these constructions, creating sentences that are comprehensible but somehow off in ways that can't be attributed to any contemporary dialect. Consider how we might react to someone who consistently omitted articles in contexts where they're required in contemporary English, or who used verbal aspect in ways that seem slightly wrong to our ears. We might attribute these patterns to interference from another language, but they could represent genuine grammatical evolution, the emergence of new patterns, or the disappearance of distinctions that currently seem essential to us. As you drift toward sleep, consider how the grammar you use without thinking would appear to someone from Shakespeare's time. How strange our simplified verb forms and fixed word order might seem. Now imagine how your own grammatical patterns might strike someone 2 or 3 centuries in the future. What complexities might they have simplified that we consider essential? What new distinctions might they have developed that our grammar doesn't express? Language flows forward through time like a river, carrying all of us with it, changing so gradually that we rarely notice its movement until we look back and see how far we've traveled from the shores of earlier forms. Beyond pronunciation and grammar, vocabulary undergoes perhaps the most visible evolution across time. New words enter the language while others fade from use. Existing words take on new meanings, sometimes dramatically different from their original senses. These lexical changes leave distinctive markers on speech from different eras, creating a potential challenge for anyone attempting to blend into a time not their own. The technological vocabulary of even 20 years ago sounds noticeably dated. Today, terms like information superhighway, cyberspace, or World Wide Web that were cutting edge in the 1990s now carry a distinctly vintage quality. Words like dial, tape, or rewind persist in our vocabulary even as the technologies that gave them meaning, rotary phones, cassette tapes, VCRs, have largely disappeared. We still hang up phones that are never physically hung anywhere, and the save icon in many computer programs remains a floppy disk that younger users have never actually seen in real life. A time traveler would need to carefully update their technological lexicon to match current usage, replacing outdated terms with contemporary equivalents. Similarly, they would need to avoid using terms that haven't yet entered common usage in our era. Words for technologies, concepts, or social arrangements that don't yet exist. They might need to suppress the instinct to use terms like artificial, general intelligence, neural interface, or quantum encryption if these concepts have become commonplace in their time, but remain specialized or futuristic in ours. Even simple terms for everyday objects change over time. What we call a refrigerator was once an icebox. What we call a car was first an automobile or horseless carriage. These shifts in common vocabulary happen gradually but definitively, creating clear temporal markers in speech and writing. A visitor from the future might need to learn not just the technical vocabulary of our time, but the everyday terms we use for objects and activities that might be named differently in their era. Slang and colloquial expressions serve as particularly strong temporal markers. Phrases like 23 skidoo, the bee's knees, or hotsy-totsy immediately place a speaker in the 1920s. Expressions like far out, groovy, or what a drag evoke the 1960s and early 1970s. The rapid turnover of slang means that even expressions from the early 2000s, bling off the hook, or talk to the hand, now sound noticeably dated. A time traveler using such expressions out of their historical context would immediately signal their displacement, while accidentally using slang from their own era terms that haven't yet been coined in our time might create even more noticeable anachronisms. Imagine the challenge of navigating contemporary slang if you came from 50 years in the future. Would you know that calling something sick or fire can be complimentary? Would you understand what someone meant by saying they were ghosted or catfished? Would you recognize terms like yeet, stan, or woke in their current usage? And how difficult would it be to avoid using slang terms from your own era that haven't yet been invented in ours? Words also change meaning over time, creating potential pitfalls for temporal visitors. The word awful once meant inspiring awe rather than very bad. Nice originally meant foolish or simple before evolving through a series of meaning changes to its current sense of pleasant or agreeable. Gay shifted from meaning carefree or bright to referring specifically to homosexuality. A time traveler might occasionally use words with their future meanings, creating confusion or misunderstanding when those senses differ from current usage. These semantic shifts often follow predictable patterns. Words frequently shift from more specific to more general meanings, generalization, or from more general to more specific, specialization. They may deteriorate in meaning pejoration, as when silly shifted from meaning blessed to foolish, or improve amelioration, as when knight evolved from meaning boy to an honored position. Understanding these patterns might help a time traveler anticipate which current words might change meaning in the future. But the specific trajectory of any individual word would be difficult to predict. Semantic broadening and narrowing represent common patterns in lexical evolution. Words like meat once referred to food in general, before narrowing to mean specifically animal flesh. Bird once specifically meant young bird, before broadening to encompass all avian creatures. Future English will undoubtedly contain many examples of words we use today that have broadened, narrowed, or shifted their meanings in ways we can't predict. A time traveler might inadvertently use these evolved meanings, creating subtle disconnections in conversation. Euphemism cycles represent another pattern in vocabulary evolution that could trip up a temporal visitor. Terms referring to bodily functions, death, disability, or other sensitive topics regularly undergo replacement as existing terms come to feel, to direct, or acquire negative connotations. The progressive substitution of passed away, departed, at rest, and similar expressions for the more direct died exemplifies this pattern. As does the evolution from crippled to handicapped to disabled to differently abled. A time traveler might use euphemisms that haven't yet emerged in our time, or might inadvertently use terms that were once acceptable but have become offensive. They might refer to concepts using terminology that, in our era, carries connotations they don't intend. The euphemism treadmill moves particularly quickly for terms relating to marginalized groups and sensitive topics. Words that were considered appropriate and respectful just a few decades ago may now be regarded as offensive or outdated. A time traveler from the future might struggle to navigate these shifting terminologies, especially if further evolution has occurred in their time. They might use terms that seem unnecessarily euphemistic to contemporary ears, or might inadvertently employ words that have acquired negative connotations in our time but have been reclaimed or replaced in theirs. Perhaps most revealing would be references and cultural knowledge. A traveler from the future might know historical events that haven't yet occurred from our perspective. In casual conversation, they might reference a future president, a war that hasn't happened yet, or a natural disaster still to come. They might mention the outcome of events currently unfolding or refer to the long-term consequences of current decisions in ways that reveal knowledge they shouldn't possess. Imagine the challenge of discussing contemporary politics without revealing knowledge of how current situations will resolve, or talking about emerging technologies without disclosing their future impact. A time traveler might need to feign uncertainty about developments they know with certainty, express concern about issues they know will be resolved, or show excitement about innovations they know will fail. This constant need to suppress actual knowledge while simulating appropriate contemporary reactions would require extraordinary mental discipline. They might reference cultural workbooks, films, music that don't yet exist. Imagine someone casually mentioning a film that hasn't been made yet, quoting from a book not yet written, or humming a tune that won't be composed for decades. These cultural references often emerge naturally in conversation as shared touchpoints, making them particularly difficult to monitor and control. A time traveler would need to become fluent in the cultural products of our era, while carefully avoiding any reference to works from their own time. This challenge would be particularly acute for popular culture, which serves as a common framework for social interaction. Understanding references to current celebrities, TV shows, viral content, or popular music would be essential for blending in, while avoiding references to future cultural phenomena would require constant vigilance. A slip might be dismissed as an original thought or creation, but a pattern of such references could create suspicion or confusion. A visitor from the future might express surprise at the absence of technologies or social arrangements they take for granted. They might reach for a device that doesn't exist yet, momentarily expect a technology to perform functions beyond its current capabilities, or show confusion at the absence of services or systems that, from their perspective, should be ubiquitous. They might react with surprise to social customs or institutional structures that have changed or disappeared in their time. Imagine someone instinctively trying to make a gesture that activates a neural interface, reaching for a pocket device that doesn't exist in our time, or expressing confusion at the need for physical keys or passwords. These small behavioral tells might be rationalized individually, but could form a pattern that marks someone as distinctly out of place. The time traveler would need to consciously suppress these instinctive behaviors while learning to navigate technologies that might seem primitive or cumbersome from their perspective. Controlling these spontaneous reactions would require constant vigilance, especially in casual conversation where conscious monitoring of speech is more difficult. Formal interactions can be carefully planned and scripted, but informal conversations flow naturally, with less conscious control. A time traveler might maintain perfect, period-appropriate language during an interview or presentation, only to slip during a casual dinner conversation or when surprised by an unexpected question. The cognitive load of this constant self-monitoring would be immense, simultaneously remembering what should not be known, suppressing reactions that would seem natural, and generating appropriate responses based on limited information. This mental strain might itself become a tell, creating patterns of hesitation, careful speech, or unusual attention to detail that could mark someone as different, if not specifically as a time traveler. For a time traveler wishing to remain undetected, the safest approach might be to speak as little as possible, to listen more than talk, and to carefully craft a persona that explains any linguistic peculiarities. They might claim to have grown up in isolation, perhaps in a religious community with limited contact with the outside world, explaining why their speech patterns differ from contemporary norms. They might present themselves as having learned English as a second or third language, attributing any oddities to interference from their supposed native tongue. Such a background would explain not just linguistic anomalies, but also gaps in cultural knowledge or unusual reactions to common situations. It might justify both archaic and futuristic elements in their speech. The former attributed to the isolationist communities preserved patterns, the latter to idiosyncratic developments within that isolated context. This cover story would provide a framework for explaining a wide range of potential temporal markers without raising suspicions of their true origin. They might claim to have a neurological condition affecting speech, such as a recovered aphasia following a brain injury, or a mild form of autism that affects their language processing. In our era of increasing awareness and acceptance of neurodiversity, such an explanation might deflect attention from linguistic anachronisms while discouraging too much questioning about speech patterns. It might also explain unusual knowledge in specific domains as savant abilities, while justifying gaps in common knowledge or social understanding. Such covers would provide plausible explanations for any temporal markers that might otherwise reveal their true origins. They would create a social buffer, making others less likely to question linguistic oddities and more inclined to attribute them to the established explanation. The time traveler might even find that people begin to accommodate their speech patterns, adapting to make communication easier, and drawing less attention to the very features that might otherwise expose them. This strategy of hiding in plain sight by providing an alternative explanation for anomalous features represents a sophisticated approach to temporal camouflage, rather than attempting perfect mimicry of contemporary patterns, a task that might be impossible given the subtle and pervasive nature of temporal markers. The traveler creates a context in which differences are expected and accepted. They transform a potential weakness into a protective shield, using our cultural expectations and social accommodations to maintain their cover. As we consider these linguistic challenges faced by potential time travelers, it's worth noting that similar issues confront historical novelists, filmmakers, and actors portraying characters from different eras. Creating authentic historical dialogue requires deep research into the vocabulary, grammar, and speech patterns of specific time periods. Even small anachronisms can break the illusion for knowledgeable audiences. The difference, of course, is that fictional depictions need only convince an audience, while a genuine time traveler would face much higher stakes in maintaining their linguistic disguise. As you rest and ponder these quiet patterns of language evolution, consider your own speech, the slang you use, your grammatical choices, the rhythm of your sentences. These elements place you in a specific moment in linguistic time, connecting you to others who share these patterns, while distinguishing you from those who came before and those who will come after. Language flows through time like a river, and all of us swim in its current, carried forward word by word, sentence by sentence, into linguistic territories our ancestors could never have imagined. Throughout history, certain technologies have appeared with surprising suddenness, leading some to speculate about external influence or knowledge beyond what should have been available at the time. These technological leaps create discontinuities in the otherwise gradual progression of human innovation, moments when our capabilities seem to advance beyond what preceding developments would predict. While conventional historical explanations usually exist parallel development, forgotten predecessors, or simply the convergence of necessary preconditions, these cases still raise gentle questions about the linearity of technological progress. The night sky is growing deeper now, the stars emerging one by one. Perhaps you're feeling the gentle weight of the day's activities, your thoughts becoming softer, more diffuse. That's perfect. Let these reflections on history's mysteries float through your mind without effort, each idea drifting like a leaf. On a quiet stream, consider the Antikythera mechanism again, not merely for its complexity, but for its apparent isolation in technological history. Discovered in a shipwreck off the Greek island of Antikythera, this device dates to approximately 100 BCE and contains an intricate system of at least 30 bronze gears. These gears work together to predict astronomical positions, eclipses, and the cycles of the ancient Olympic Games with remarkable precision. Its mechanical complexity would not be matched in Europe until the development of astronomical clocks in the 14th century. Over 1,400 years later, when first discovered in 1901, the mechanism appeared to be little more than a corroded lump of bronze and wood. Only decades later, as imaging technology improved, did researchers begin to appreciate its true complexity. X-ray analysis and advanced scanning techniques gradually revealed the intricate gearwork hidden within the encrusted remains. Each new examination uncovered further details, inscriptions, additional gears, mechanisms for modeling complex astronomical cycles, painting a picture of technological sophistication far beyond what historians had previously attributed to ancient Greek civilization. The Antikythera mechanism could track the Metonic cycle, a 19-year pattern after which the phases of the moon repeat on the same calendar dates. The Saros cycle, an 18-year pattern used to predict eclipses, and even the variable orbital speed of the moon, what astronomers call lunar anomaly. It could predict the positions of the 5 planets known to the ancient Greeks and account for the irregular apparent motion of these bodies as viewed from Earth. All this was accomplished through mechanical computation gears of different sizes, turning at precise ratios to model celestial movements with remarkable accuracy. This sophisticated calculator emerged from a cultural context that had certainly developed considerable mathematical and astronomical knowledge, but had not, as far as we know, created comparable mechanical devices. The mechanism appears almost without precedent, a technological flower blooming without visible roots. After its creation, around 100 BCE, similar mechanical computing devices don't appear in the historical record for well over a millennium. It's as though someone briefly introduced a technology far ahead of its time, only for it to disappear again until society caught up. Conventional explanations suggest that similar devices might have existed but were lost or destroyed, their bronze components melted down for other uses during times of scarcity. Perhaps the knowledge was preserved in limited circles, passed from master to apprentice through generations without leaving written records, before being rediscovered and further developed during the Renaissance. These explanations are certainly plausible. Bronze was valuable, and much of ancient technical knowledge was transmitted orally rather than in writing. Yet the gap remains striking. Why would such a useful technology not spread more widely? Why would the knowledge of its construction not be preserved in the extensive writings of the Hellenistic and Roman periods? How did the creators make such a remarkable leap in mechanical precision without leaving evidence of the intermediate steps in development? The mechanism stands as a whisper across time, raising gentle questions about the linearity of technological progress. Historical records offer some context, but no complete explanation. The Greek mathematician and engineer Archimedes is known to have created complex mechanical devices, including a planetarium that showed the movements of the sun, moon, and planets. The Roman statesman Cicero described this device, writing that it showed the moon, sun, and 5 planets in their respective orbits, much like the Antikythera mechanism. Yet Archimedes' device has not survived, and we have no detailed descriptions of its internal workings. Was the Antikythera mechanism part of a broader tradition of such astronomical calculators? Or was it a rare achievement, perhaps the work of a single brilliant inventor whose knowledge died with them? As you breathe slowly and deeply, imagine holding this ancient device in your hands, the weight of its bronze components, the precision of its gears, the quiet clicking as you turn the input knob. Imagine the hands that crafted it over 2,000 years ago, the mind that conceived its intricate design. What were they thinking as they aligned those gears? Did they realize they were creating something that would not be matched for over a millennium? Did they see themselves as preserving knowledge, advancing it, or simply applying what was, to them, conventional wisdom now lost to us? The development of Egyptian pyramids presents another curious case in the history of technology. The Great Pyramid of Giza, built around 2560 BCE, exhibits mathematical and engineering precision that seems to emerge with remarkable suddenness in the archaeological record. While Egypt had a tradition of monumental architecture stretching back centuries before the Great Pyramid, including earlier structures like the Step Pyramid of Djoser, built around 2630 BC, the leap in technical sophistication remains remarkable. The Great Pyramid's base is level 2 within just 2.1 centimeters, despite covering 13 acres, and its sides are aligned to the cardinal directions with an accuracy of up to 0.05 degrees. The massive limestone blocks, some weighing over 50 tons, were cut with such precision that the seams between them are often barely visible. The internal chambers and passages maintain precise angles and alignments throughout the massive structure. The pyramid incorporates sophisticated engineering features, like stress-relieving chambers above the king's chamber that distribute the enormous weight of the overlying stone, preventing collapse. These achievements become even more impressive when we consider the tools available to the ancient Egyptians, primarily copper chisels, stone hammers, wooden levers, and ropes. Without iron tools, power equipment, or modern surveying instruments, they achieved a level of precision that would challenge even contemporary builders. The logistics of quarrying, transporting, and placing an estimated 2.3 million stone blocks, each weighing an average of 2.5 tons, represents an organizational feat as impressive as the engineering itself. Conventional archaeology traces the development of these techniques through earlier structures and the evolution of Egyptian knowledge. The Third Dynasty Step Pyramid of Djoser shows the early development of monumental stone architecture. The Fourth Dynasty Bent Pyramid demonstrates an intermediate stage in the development of true pyramid construction, its angles changing partway up in what appears to be a correction to an overly ambitious initial design. This suggests a process of learning and adaptation rather than fully formed knowledge from the beginning. Yet even with this developmental sequence, the precision achieved in the Great Pyramid still impresses modern engineers. The astronomical alignments, the accuracy of the stone cutting, the sophisticated understanding of structural stability, All these suggest a level of knowledge that seems to have matured with remarkable speed. How did the ancient Egyptians achieve such precision without modern surveying equipment? How did they cut and move such massive stones with such accuracy, using only copper tools and human labor? Various theories have been proposed to explain these achievements. Ingenious uses of water levels for establishing flat surfaces, astronomical observations for alignment, clever ramp systems for moving heavy stones. All these methods are plausible within the technological context of ancient Egypt. Yet the question remains, how did this knowledge develop so rapidly? And why did some aspects of it seem to fade in later periods rather than continuing to advance? Later pyramids, while still impressive, generally show less precision and quality than those of the Fourth Dynasty, particularly the Great Pyramid itself. This pattern of decline, rather than continued advancement, presents a puzzle. Was developed internally through generations of Egyptian experimentation. Why would it not continue to improve, or at least maintain its peak level? Some have suggested that the immense resources required for such precise work became unsustainable, or that political instability disrupted the transmission of specialized knowledge. But the pattern remains: rapid rise to extraordinary achievement, followed by gradual decline, rather than the steady improvement we might expect from an evolving technological tradition. As your body settles more deeply into rest, imagine standing in the shadow of the Great Pyramid, feeling the smooth surface of its limestone casing blocks, now mostly removed, but originally covering the entire structure. Feel the perfect joins between the stones, the mathematical harmony of its proportions. What hands placed these stones so precisely? What minds calculated these alignments with such accuracy? Their achievement speaks across millennia, a reminder that human ingenuity often advances in unexpected leaps rather than steady, predictable increments. More recently, the development of nuclear physics in the early 20th century proceeded with surprising rapidity. While built upon previous scientific discoveries, the pace from theoretical understanding to practical application was remarkable. From Einstein's formula E equals mc in 1905, which established the equivalence of mass and energy, to the first controlled nuclear chain reaction achieved by Enrico Fermi in 1942, to the development of the atomic bomb in 1945, the timeline represents an extraordinarily compressed period of scientific and technological development. Consider the sequence of discoveries that led to this breakthrough. In 1896, Henry Becquerel discovered radioactivity. In 1898, Marie and Pierre Curie identified radioactive elements, radium and polonium. In 1911, Ernest Rutherford proposed the nuclear model of the atom. In 1932, James Chadwick discovered the neutron. In 1938, Otto Hahn and Fritz Strassmann achieved nuclear fission. And by 1945, a fully functional nuclear weapon had been designed, built, and detonated. In less than 50 years, humanity went from discovering the basic phenomenon of radioactivity to harnessing nuclear energy for both destructive and eventually constructive purposes. This acceleration is generally attributed to the pressures of World War II and the concentration of scientific talent in the Manhattan Project. When resources are abundant and motivation is high, technological development can indeed proceed at remarkable speeds. The project brought together the finest minds in physics, provided them with nearly unlimited resources, and gave them a clear, urgent objective. Under such conditions, the rapid development of nuclear technology becomes more understandable. Yet it remains one of the most dramatic technological leaps in human history, from a theoretical understanding of atomic structure to harnessing the fundamental forces of the universe in less than half a century. The gap between theoretical knowledge and practical application was bridged with remarkable speed, raising questions about the usual pace of technological development. Was this simply what happens when human ingenuity is focused with sufficient intensity on a single problem? Or might other factors have accelerated this particular technological leap? The development of nuclear technology also presents an interesting case of simultaneous discovery. Teams in multiple countries were working toward similar goals during the same period, suggesting that once certain theoretical and experimental foundations were established, the pathway to nuclear energy became almost inevitable for any sufficiently resourced scientific community. This pattern of simultaneous innovation appears repeatedly in technological history, from calculus, developed independently by Newton and Leibniz, to evolutionary theory, Darwin and Wallace, to the telephone bell, and Gray filed patents on the same day. These convergences suggest that certain discoveries occur when the necessary preconditions align, regardless of individual inventors. As your thoughts drift gently in the growing stillness of night, imagine being present in the New Mexico desert on July 16, 1945, as the first atomic bomb was detonated. The flash of light, brighter than any ever created by humans, the distinctive mushroom cloud rising into the atmosphere, the shock wave rippling outward across the landscape. In that moment, humanity crossed a threshold, harnessing fundamental forces of nature that had previously lain beyond our reach. The physicist J. Robert Oppenheimer, watching the explosion, recalled a line from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." The technology that emerged in that desert would transform geopolitics, reshape international relations, and create both new threats and new opportunities for human civilization. These examples and others, like them, can be explained through conventional historical processes: the accumulation of knowledge, the pressures of necessity, the occasional inspired insight, and the tendency of historical records to simplify complex developmental paths. The gaps and leaps in the historical record don't necessarily indicate outside influence or knowledge from beyond their time. Human ingenuity often exceeds our expectations, making connections and discoveries that seem premature when viewed from a distance. Yet they remind us that technological progress is not always as linear or gradual as we might expect. Breakthroughs sometimes appear with surprising suddenness, as though history occasionally skips ahead. These discontinuities in technological development create space for speculation. Could some of these leaps represent knowledge transferred from the future? Might time travelers, whether deliberately or accidentally, have introduced concepts or techniques before their natural emergence in the timeline? Such speculation remains firmly in the realm of science fiction rather than science. The conventional explanations, parallel development, forgotten predecessors, the convergence of necessary preconditions. The accelerating effect of focused resources provides sufficient frameworks for understanding these technological leaps without invoking temporal interference. Yet the pattern of occasional discontinuities in technological progress creates an interesting thought experiment. If time travelers did visit earlier periods, their influence might manifest not as obvious anachronisms, but as subtle accelerations of developments already underway. Technological flowers blooming slightly ahead of their expected season. If time travelers were to visit our era or earlier times, what ethical principles might guide their interactions with the past? This question has fascinated science fiction writers for generations, producing rich explorations of the moral complexities involved in temporal displacement. Beyond entertainment, these fictional treatments raise genuine philosophical questions about responsibility, intervention, and the nature of history itself. Fiction has often explored the concept of interference, the idea that time travelers should observe but not alter past events. This principle, sometimes called the temporal prime directive in reference to Star Trek's non-interference policy, recognizes the potentially catastrophic consequences of changing history. These consequences might include logical paradoxes, where cause and effect become hopelessly entangled, or butterfly effects, where small changes cascade into major historical alterations that the time traveler could neither predict nor control. The butterfly effect, named after the metaphorical concept that a butterfly flapping its wings in Brazil might eventually cause a tornado in Texas, captures the sensitive dependence on initial conditions that characterizes complex systems. In the context of time travel, it suggests that even the smallest intervention in the past, a conversation with a stranger, the prevention of a minor accident, the introduction of a seemingly inconsequential idea might ripple forward through time, causing progressively larger deviations from the original timeline. These compounding changes could eventually create a future dramatically different from the one the traveler left behind. Imagine a time traveler who prevents a minor traffic accident in 1950. This seemingly benevolent act might save the lives of those involved, but it could also mean that a child who would have been conceived later because of delays caused by the accident is never born. Perhaps that unborn child would have grown up to make a crucial scientific discovery or political decision. Or perhaps one of the accident survivors goes on to commit a terrible crime. The web of causality, extending from even minor events, becomes infinitely complex as time passes, making the consequences of interference impossible to calculate fully. A formal version of this principle might be something like the temporal prime directive, a prohibition against interfering with the natural development of past societies. Under such a directive, time travelers would be permitted to observe and record, but not to intervene, even in cases where intervention might prevent suffering or advance development. They would be historians, not actors. In the drama of the past, this strict non-interference policy has a certain ethical elegance. It respects the integrity of history and the autonomy of past societies to develop according to their own internal dynamics, without manipulation from future actors possessing advantages of knowledge and technology. It avoids the moral hazard of time travelers appointing themselves judges of which historical developments should be preserved and which altered. It acknowledges the limits of human foresight. even when enhanced by historical knowledge. From a certain philosophical perspective, the past has already happened and therefore possesses a kind of integrity that deserves respect. Changing it might be seen as violating this integrity, as attempting to rewrite a story that has already been told. If we view time as a fourth dimension, similar to the three dimensions of space, then changing the past might be analogous to erasing part of existence itself, not merely altering events, but undoing them completely, along with all their consequences. This perspective suggests that the past possesses a kind of ontological status that creates ethical obligations toward its preservation. Yet strict non-interference presents moral challenges that would test the resolve of any time traveler. Imagine witnessing a preventable disaster, a building fire, a shipwreck, a car accident, knowing that dozens or hundreds of lives could be saved through simple intervention. Could one ethically stand by and watch a tragedy unfold, knowing it could be prevented? The moral weight of such inaction might prove unbearable, particularly for a traveler with no personal investment in maintaining the purity of the timeline. Consider a time traveler who finds themselves in Krakatoa just before the 1883 eruption, or in Pompeii before Vesuvius erupted in 79 CE. They possess knowledge that could save thousands of lives by evacuating the area before disaster strikes. Would the principle of non-interference require them to remain silent, allowing these deaths to occur because they are supposed to happen? The ethical calculus becomes even more challenging when we consider that these natural disasters are not integral to human historical development in the way that human-caused events might be. Preventing them would not seem to violate human autonomy, or interfere with societal self-determination, or consider larger-scale suffering. A time traveler in Europe during the Black Death might possess knowledge of basic sanitation and quarantine procedures that could save millions of lives. One in 1930s Germany might recognize the early signs of the Holocaust and have opportunities to warn potential victims or undermine the rising Nazi regime. Could one ethically withhold such intervention, allowing historical atrocities to unfold? For the sake of timeline preservation, these questions evoke the philosophical trolley problem and other ethical dilemmas that pit consequentialist ethics, judging actions by their outcomes, against deontological ethics, judging actions by their adherence to rules or duties. A consequentialist might argue that preventing suffering is always the higher moral duty, regardless of temporal considerations. A deontologist might counter that maintaining the integrity of history constitutes a higher obligation that supersedes even the prevention of immediate harm. Perhaps a more nuanced ethical framework would allow minimal interventions in cases of imminent harm to individuals, while still prohibiting larger-scale alterations to historical events. Under such guidelines, a time traveler might pull a child from the path of a speeding carriage, or warn a family about a structural weakness in their home, but would refrain from preventing wars, assassinations, or natural disasters that shaped the broader course of history. This compromise position acknowledges the moral imperative to prevent suffering when directly confronted with it, while still respecting the general principle that history's larger patterns should not be subject to manipulation. It recognizes that time travelers are moral agents who cannot entirely suspend their ethical responsibilities simply because they are displaced in time. while still maintaining appropriate humility about their right to reshape historical developments. The framework might include principles like 1. Intervention is permissible to prevent immediate harm to individuals with whom the traveler directly interacts. 2. Intervention should be minimized, using the least disruptive means available. 3. Large-scale historical events should not be deliberately altered. 4. Knowledge of future developments should not be shared broadly or used for personal gain. 5. The traveler should attempt to minimize their overall impact on the timeline. Such principles would allow for compassionate action in the face of immediate suffering, while maintaining respect for the broader integrity of historical development. They would recognize both the moral agency of the time traveler and the moral significance of temporal continuity. Alternatively, time travelers might adopt something like the minimal ripple approach, making changes only when necessary and in ways designed to minimize disruption to the overall timeline. This might involve behind-the-scenes actions that preserve the outward appearance and outcomes of historical events while subtly altering details. A time traveler might, for instance, save an individual from a disaster without changing the disaster itself, or introduce a technology in a limited way that doesn't dramatically alter historical development. Imagine time traveler. Who knows? A particular family will die in a building collapse during an earthquake. Rather than preventing the earthquake or evacuating the entire region, which would create massive ripples in the timeline, they might engineer a situation that ensures just that family is elsewhere when disaster strikes. Perhaps they create a job opportunity that takes the family out of town, or arrange for a minor household problem that requires them to stay with relatives. The disaster still occurs as recorded in history. The overall death toll remains similar, but specific individuals are saved through subtle intervention. This approach resembles the fixed timeline theory, sometimes explored in fiction, where time travelers discover that their interventions in the past were actually part of history all along. Perhaps the anonymous warning that saved a family from a fire was always delivered by a time traveler. Perhaps certain technological innovations or scientific insights were always introduced ahead of their natural schedule by visitors from the future. In this view, time travel doesn't change history but fulfills it, creating a coherent, self-consistent timeline where past, present, and future form a unified whole. This model resolves certain logical paradoxes by suggesting that time travel creates loops of causality rather than changes to an original timeline. The classic bootstrap paradox, where an object or information has no discernible origin because it's caught in a temporal loop, becomes not a problem but a feature of how time functions. In this framework, a time traveler who goes back to give their younger self the plans for a time machine isn't changing history but completing a causal loop that was always part of reality. The minimal ripple approach offers an elegant solution to some ethical dilemmas, allowing for compassionate intervention while maintaining historical integrity. However, it requires both extensive historical knowledge and extraordinary subtlety to implement successfully. How can a time traveler be certain which changes will ripple outward significantly and which will remain contained? The butterfly effect suggests that even tiny alterations might have massive long-term consequences, making truly minimal ripples difficult to guarantee. Some theoretical frameworks for time travel sidestep these ethical dilemmas entirely. If time travel creates new timelines or alternate realities, as suggested by the many worlds interpretation of quantum mechanics, then travelers would not be altering their own past, but creating a new branch of reality. In this model, a time traveler who prevents a disaster doesn't change the past, but creates a new timeline where the disaster didn't occur, while the original timeline continues to exist separately. This framework draws on Hugh Everett's many worlds interpretation of quantum mechanics, which suggests that quantum events create branching timelines rather than collapsing probabilistic wave functions. Each possible outcome of a quantum event occurs in its own separate reality, creating an ever-branching multiverse of parallel worlds. Time travel might operate according to similar principles, with each intervention creating a new branch of reality rather than altering an existing timeline. In such a framework, the ethical constraints might be quite different, focusing more on responsibility to the newly created timeline than preservation of one's original history. Time travelers would not need to worry about paradoxes or timeline corruption, but they would bear moral responsibility for the new branch of reality they create through their interventions. They would, in effect, become founders of new historical paths. With all the ethical weights such influence carries, this multiverse approach resolves many logical paradoxes of time travel, but introduces its own ethical complexities. If new timelines are created through temporal intervention, does the time traveler have a responsibility to optimize these new realities according to certain moral principles? Should they attempt to create the most just, peaceful, or prosperous alternative timeline possible? Or should they still exercise restraint, allowing the new branch of history to develop according to its own internal dynamics once the initial intervention is complete? There's also the question of the traveler's relationship to the new timeline. If they remain in this branch, they become part of the reality they've created, experiencing its consequences alongside everyone else. This creates a kind of natural accountability. The traveler cannot simply create changes and then escape their effects by returning to their original timeline. They must live in the world they've helped shape, providing a natural check against irresponsible intervention. For time travelers practicing non-interference, observation itself would become an art form. They might develop sophisticated techniques for unobtrusive monitoring technologies that allow them to watch without being watched, to record without leaving evidence of their presence. They might use remote viewing devices, miniaturized cameras, or advanced cloaking technologies to observe historical events without being detected by contemporaries. These technologies might include passive sensors that detect light, sound, and other emissions without generating signals that could be detected by period technology. They might incorporate adaptive camouflage that mimics surrounding materials, or quantum observation techniques that somehow extract information without classical interaction with the observed system. For periods with limited surveillance capability, most of human history, even relatively simple concealment might suffice, while observation of more recent eras with sophisticated detection technology might require more advanced approaches. They might master the social skills needed to blend into past societies, becoming invisible not through technology but through perfect cultural adaptation. This would require extensive preparations, studying the clothing, mannerisms, speech patterns, and social norms of the target period until they could move through it without attracting attention. They might establish false identities with plausible backgrounds, creating paper trails and personal histories that would withstand the level of scrutiny typical for their chosen time and place. This social camouflage might involve adopting roles that provide natural access to events of interest, while minimizing scrutiny. Servants in great houses, clerks in government offices, maintenance workers in significant buildings. These positions often combine access with invisibility, allowing observation without drawing attention. Alternatively, roles that involve expected movement between social contexts, merchants, messengers, entertainers, might provide opportunities to observe multiple settings without arousing suspicion. They might establish observation posts at key historical junctures, creating a network of temporal historians documenting the true course of events, rather than relying on the often incomplete or biased accounts that survive in conventional historical records. These observation posts might be staffed by rotating teams of temporal researchers, each spending months or years in the past, before returning to their home time with their observations and records. Such a network might focus on historically significant locations during critical periods: Athens during the Golden Age, Rome during the transition from republic to empire, Constantinople during its fall to the Ottoman Empire, Philadelphia during the Constitutional Convention. These posts would maintain rigorous protocols to minimize their historical footprint, while maximizing the quality and comprehensiveness of their documentation. As you drift toward sleep, imagine such observers moving quietly through history, the construction of the pyramids, witnessing the debates of the Constitutional Convention, documenting daily life in ancient Rome or Song Dynasty China. Imagine them taking careful notes, recording images and sounds, preserving the textures and rhythms of times now lost to conventional history. Their observations would create a remarkable archive, a direct window into periods we know only through artifacts and written records. These ethical considerations raise profound questions about the nature of history itself. Is the timeline, as we know it, sacred, something to be preserved at all costs? Or is history more malleable, open to improvement through careful intervention? Do we have moral obligations to past generations that might override other ethical considerations? Does knowledge of the future create special responsibilities that transcend normal ethical frameworks? Time travel remains firmly in the realm of science fiction, yet these questions touch on very real ethical dilemmas. How much should we intervene in other societies? When is it appropriate to impose our values and knowledge on cultures different from our own? What responsibility do we bear for foreseeable but unintended consequences of our actions? The temporal element adds unique complexities to these questions, but the fundamental ethical tensions are ones we face even in our ordinary linear experience of time. As the night deepens around you, allow these ethical questions to settle gently. In your mind, there are no simple answers, no clear formulas that resolve all the moral complexities of temporal intervention. Perhaps that ambiguity is fitting. Ethics rarely offers perfect clarity, especially when we venture into territories as strange and unfamiliar as time travel. The questions themselves may be more valuable than any definitive answers, inviting us to reflect on our responsibilities to past, present, and future generations, and on the complex web of consequences that flows from every action we take. If future civilizations develop time travel, why might they send observers to our particular era? What makes the early 21st century worthy of temporal reconnaissance? These questions invite us to view our own time through the lens of historical significance, to consider which aspects of our era might hold particular interest or value for future societies. From a historical perspective, our time represents a period of remarkable transition and acceleration. We stand at the confluence of several transformative developments: the digital revolution, climate change, the emergence of artificial intelligence, genetic engineering, and the beginnings of space colonization. Future historians might view this period as a critical juncture in human development, a time when several possible futures branched from a common present. The digital revolution represents perhaps the most visible transformation of our era. In just a few decades, we have moved from a world where computers were rare, specialized devices, to one where powerful computing technology is ubiquitous, embedded in everything from phones to refrigerators to children's toys. We have created a global network of unprecedented scale and complexity, allowing near-instantaneous communication and information sharing across the planet. We have begun digitizing our cultural heritage, creating vast archives of text, images, sound, and video accessible to anyone with an internet connection. This transformation has reshaped how humans interact, how we access and process information, how we conduct commerce, how we create and consume art, how we participate in politics virtually. Every aspect of human activity has been touched by this technological revolution. Future historians might see this period as comparable to the development of writing or the printing press in its impact on human society, a fundamental shift in how information flows and how people connect with one another. Future historians might be particularly interested in documenting the social and psychological impacts of this transformation. How did the sudden availability of unlimited information affect human cognition and social structures? How did the emergence of social media reshape community formation, political discourse, and personal identity? How did societies adapt to the unprecedented transparency and surveillance capabilities created by digital technologies? These questions might be difficult to answer based solely on the digital records that survive into the future, making direct observation of our era valuable for temporal researchers. While our time generates enormous volumes of data, much of it might prove ephemeral or inaccessible to future researchers. Digital storage formats become obsolete, online platforms shut down, encryption becomes unbreakable, or keys are lost, proprietary formats become unreadable. The paradox of our information age might be that despite generating more records than any previous era, we could leave fewer permanent, accessible traces than civilizations that carved their records in stone. Time travelers might seek to preserve information that would otherwise be lost to format obsolescence or digital decay.